Hello everyone. Today we'll start with the numericals of moment distribution method. In last video lecture, we have seen some basic concept for your moment distribution method, like as what is the value of df, how we calculate that, okay, formula of that, carryover factors, carryover moments, and the relative stiffness for calculating distribution factors we have seen. Okay. Now using those concepts, you have to solve the numericals on beams and sway and non-sway frames using moment distribution method now. Okay. So we'll start with your first numerical. You'll see here it is asked you to calculate the final support moments of a continuous beam using MDM. MDM is nothing but moment distribution method. A continuous beam is given to, suppose A, B and C with certain loading on this. Okay. Joint A is fixed one, and while joint B and joint C is your roller supports are given. Okay. So as per these supports, you have to classify these supports into two different types, that is capable support and incapable support. Regarding that, we have seen how to classify the capable and incapable support in our last video lecture. Okay. So if you want to see, you watch that video again to note that. Okay. So first initial step, that is what, this is again a stiffness method, okay, or displacement method. So firstly what you have to do, you have to calculate the value of dk here. Okay. So dk, for this I will see for support condition A is fixed on, so here dk value will become 0, theta b and theta c will be your two dk values. So total dk I am getting here equal to 2, that is theta b clockwise rotation and theta c as initial I am assuming that those rotation in clockwise direction. Okay. So these two will be my basic unknowns. Okay. Basic known values are what, that is theta a will be equal to 0. So this will be my basic known, while this will be my basic unknown value, which you have to calculate this theta b and theta c. Okay. Now second step, that will remain same as your slope deflection method, that is you have to calculate the fixed end moments over there. You have to calculate the fixed end moments over there. Okay. So fixed end moment as per your that fixed end moment table over there, same in same way you have to calculate that your first fixed end moment will be your MFAB. So MFAB, see, considering both of these supports as your fixed one, and what you have to do, UDL is given to you in this. Okay. So for UDL, this fixed end moment comes equal to minus WL square divided by 12. W is 25, length of AB member is 6 divided by 12. So that comes equal to, fixed end moment equal to minus 75 kilonewton meter over there. Okay. Okay. Then second fixed end moment, that will be your MFBA, so that will remain plus WL square divided by 12, and that comes equal to plus 75 kilonewton meter. Same way I will calculate for next member, that is MFBC, given loading, point load at the center. So fixed end moment comes equal to minus WL divided by 8, so that comes equal to, if you calculate, W is 100, length is your 4, so 100 into 4 divided by 8, you will get that as 50 kilonewton meter. Negative, since restoring moment will be anti-clockwise in nature. And last MFCB, that will be plus WL divided by 8, so that I will get as plus 50 kilonewton meter. So these four fixed moment values I am getting here. Okay. Now nextly, now we are in slope deflection method. What we are doing, your third step was your slope deflection equations were there. Okay. Now here there is no slope deflection equation, so here you have to calculate the moment by using distribution factors over there. So your next step, third, will be what, that will be distribution factors. Okay. So distribution factors you have to calculate. For distribution factors, what you have to see, whether your supports are capable or incapable of resisting moments or not. Okay. So for this you have to prepare one table in this, you see properly over here, that is in the table your first column, that will be your joint. Joint means what, the supports over there, that is support A is a type of joint, support B is a type of joint, and support C is also a type of joint over there. So first column, that will be your joint. Okay. After this, your second column will be members. Okay. Members meeting this particular joint. Okay. Then the third column will be your relative stiffness. Third column will be your relative stiffness. I will mark that as K. Okay. Then the next column will be your total stiffness. I will mark that as summation of K. And the last column will be your distribution factor. Formula for that we have written. It is nothing but relative stiffness of a member, that is K, divided by total stiffness of all the members meeting at that joint over there. So this will be a complete table. In every numerical you have to follow the same table. That is, first column will be your joints, second is member, third is relative stiffness K, next is total stiffness summation of K, and last is your distribution factor is equal to K divided by summation of K. So this table you have to remember over there. Okay. Now while considering joints, what you have to do, you have to not consider all the joints over here. Okay. You have to consider such joints at which two or more than two members are meeting. For single jointed members, you have to not consider those in this joint over there, because for single joint member your distribution factor, it is always equal to 1. Remember what I am saying, that for single joint member, that is, if you see joint A over here, this joint A is having only one member, that is AB. So that what happens, for this member AB, here this distribution factor will remain equal to 1 over there. Okay. So that thing you have to check over here. Okay. That is, distribution factor for single jointed member, it comes always equal to 1, and for remaining joints, that is, which is having two or more than two members, for that you have to calculate the distribution factor. So while considering here the joints, what you have to do, you have to consider only those members which are having you have to consider only those joints which are having two or more than two members over there. Okay. So such type of joint is here B, because A joint is also having one member and C joint is also having only one member. So what I am doing, I am considering my joint B. Members meeting joint B are what? Joint B is meeting member BA and BC. So these two members I am writing here. First member is BA and second member is BC. While writing here, always whatever joint you are writing here, that joint will reflect as your near end over there, and this second initial, that will be your far end. Means if you consider B a member from joint B, so B will be your near end and A will be your far end. Same way here B will be your near end and C will be far end. So while transferring moment from B to C and from B to A and B to C, what you have to check, whether support A is capable or whether support C is capable or not. You have to check always the farther end over there. While seeing the concept, we have seen this. Okay, that is, your farther end is capable or farther end is incapable over there. Now we will see first member over here, that is member BA. What is happening? Moment is getting transferred from B to A, so A will be here farther end over there. Now you check A member over here. A is what? Support condition. A is here fixed one, so fixed support is considered as your capable support. So for capable support, here this relative stiffness value, it comes equal to I divided by L. It comes equal to I divided by L. Now if you see in numerical, for this member AB, I value is given to equal to 2I. If these values are not given, it will remain same as it is, but here it is given 2I. So this I value I am writing as, that is 2I divided by length of member AB is 6. So 2I divided by 6, that is 1 by 3, I will get this equal to 0.33 times of I. Getting this? Then next member we will see now, for member BC. Moment is getting transferred from B to C, so C will be your farther end over here. Now you check C. C is what? It is the end roller or end hinge support over there. Okay. So what type of support this will be? This will be classified as your incapable support. So for incapable support, your relative stiffness value, it is equal to 3 by 4 of I by L. Now you check I value. I value for member BC is given again 1 here. Okay. So that I will remain as it is. So this becomes here equal to 3 by 4 of I divided by length of member is BC is 4. So this becomes 3 by 16. So 1 by 3 by 16 if you calculate, that I get equal to 0.187 of I. You check this value, I get that as 0.187 of I over there. Okay. Now then you have to calculate the total stiffness. Total stiffness is what? It is the stiffness or relative stiffness which is considered directly for the joint over there. So whatever number of members are meeting at this particular joint over there, you have to add all the relative stiffness to get the total stiffness. So addition of these two members, that is 0.33I and 0.187I, I get that equal to 0.52 of I over there. Okay, you try to check this. Okay, approximately you will get 0.52 of I over this. Okay, now next is your DF. DF is what? It is the value of relative stiffness to total stiffness. So if I want to calculate the DF for BA member, so how much it will be? That is BA K divided by summation of K, that is 0.33 I divided by 0.52 of I, that I gets equal to 0.63. I will get cancel over here. So in DF it is always a numerical term over there. There will be no constant term in this. So DF will be equal to 0.63, and for BC same way I will get equal to 0.187 divided by 0.52, that is K divided by summation of K. So this I gets equal to 0.37, and always remember you have one check for this, that is this DF value for every joint, means how many members are given over here. If there are 2, 3, 4, 5, the number of members, for all the members whenever you are calculating this DF at a particular joint, this DF value must remain always equal to 1, not greater than 1 nor less than 1. This will be always equal to 1 over there. Okay, so if you check this 0.63 plus 0.37, you will get that equal to 1, plus minus 0.1, 0.01 will get over there. So here you will, maybe you get 0.99 or 1.01 you will get. So that is acceptable, you can write that as 1 over there. Okay, so always remember DF for a particular joint, it will be equal to 1 regardless how many members are meeting to that. Okay, so I hope you are understanding this concept. So distribution factor for BA I am getting 0.63, and for BC I am getting equal to 0.37 over there. Okay, now using these distribution factors, what you have to do is you have to calculate the support moments over there. Okay, so your next step after distribution factor, that will be your fourth step, it will be moment distribution table you have to do. Moment distribution table. Okay, in this you have to do the distribution of moments to capable supports towards the capable supports using this distribution factors over there. Okay, now here also you are having one more table. So one table is done of distribution factor, you have to remember this second table now. Okay, so in this table what you have to do is first row, whatever you are going to consider, that will consider all the joints over here. Okay, so if you are having the joints in this, how many joints are there? A, B and C, all these joints will be considered over here. So first joint will be suppose my joint A, second will be my joint B, and third joint will be my joint C over there. So this will be my table for moment distribution. Okay, next after the joint what you have to do is you have to consider the members meeting these joints over there. Okay, all the members. So member meeting joint A is your AB member. Okay, now for B you are having two members over there, first is BA and second is BC. So here I am writing BA and second member I am writing as BC. Getting? Then next C member, you are having only one member, that is CB. So this will be my second row in this, that is members meeting these particular joints. Okay, then after that what you have to do is you have to write the distribution factors you have calculated over there. So I am writing here just DFs over there. Okay, so DF you have calculated for BA and BC member. So for BA you are getting 0.63 and for BC you are getting 0.37. So I am writing here 0.63 for BA and 0.37 for BC. While single jointed member, your distribution factor will remain always equal to 1, as I have told you earlier. Okay, then after DF you will be writing the fixed end moments over there. You have calculated that in this step. Okay, so here first I am getting as minus 75, then BA I am getting as plus 75. Okay, next is BC I am getting as minus 50, and last CB I am getting as plus 50 over there. Okay, so these four rows in your every numerical will remain common. That is, first row is your joint, second row is your members, third row is your distribution factors, and the fourth row is your fixed end moments. In any numerical, these 4 rows will not get changed. So you have to by heart, or you have to remember this 4 rows over there. First is joint, members, after that df, and last is your fixed end moments over there. Okay. Now after writing these fixed end moments, what you have to do is, the first thing is you have to balance the moment. Now balancing the moments means what? In this particular given beam over there, you have to check which support is capable and which support is incapable over there. Like as we are checking in slope deflection method, that is your conditions of equilibrium over there. Okay, conditions of equilibrium, what we are saying, at a particular joint that moment will remain 0. That is, if I say that you are at, see, if you check your conditions of equilibrium over here, you will get first condition at B, that is MBA plus BC will be equal to 0, and second condition will be at C, that is MCB will be equal to 0. So firmly I can say that my MCB will be remaining 0. That means what? If you check your capable and incapable supports also, here joint A is the fixed support, so that will be your capable support. Joint B is your, see here I am writing as capable support. Okay. Then joint B, if you see, this is what? Intermediate hinge support over there, or intermediate roller support over there. So this will be also classified as your capable support. You can check theory also. In previous lecture we have seen that. And the last is what? This is the end roller support over there. So this type of support is always classified as incapable support over there. So balancing the moment means what? For this incapable support, that is for MCB member, you are getting certain value of this moment over there. Okay, that is this plus 50, but it is incapable to resist this moment over there. So first thing what you have to do, you have to balance that moment to 0. That means you have to make this moment equal to 0 over there. So how I will make this moment 0? By applying a negative moment of minus 50 over there. So if I check plus 50 minus 50, that will become 0. Okay. Okay. Now out of this minus 50, what will happen? This CB member is somewhat joined to this joint B also. Okay. That means what? Here your carryover factor will come into effect over there. That means if from transferring moment from C to B over there, this B joint is what? It is the capable support. That means here your carryover is possible over there. Okay. So after the balancing, next part comes your carryover over there. You can write CO, or you can write complete name also, carryover there. Okay. Now carryover factor is how much? That comes equal to 1/2 over there. That means whatever moment you are considering for joint CB, for joint C in member CB, out of that half of the moment will get carry over to BC over there. Okay. So that comes equal to negative 25 over there. Okay. So understand this, if you are having any moment at your incapable support, first what you have to do, you have to balance that moment to 0, okay, by applying a negative moment, and out of that moment half of the moment will get carried out to its previous or next support over there, capable support, you remember. Okay. So from this what I get is that is the initial moments over there. These are not the final moments yet. Firstly what I am doing, I am calculating the initial moments only. Okay. So whatever these values are there, that is minus 75, it will remain as it is. Okay. Here what I am getting, plus 75. Okay. Here what I am getting, minus 50 minus 25, I will get that as minus 75, and this minus 50 plus 50, that will become equal to 0 over there. Okay. Now what you have to do, you have to distribute these further, these moments which you are calculating to your capable supports over there. Now while distributing, what you have to do, you have to add these two moments. Whatever factor you will get after adding, you have to multiply it with these distribution factors and distribute it accordingly to BA and BC over there. But if you see here, whenever you add these two moments, that is plus 75 and minus 75, this complete factors becomes here equal to 0 over there. This complete factors becomes equal to 0 over there. That means your distribution will not be further possible over there. So whatever initial moments I am getting, those are nothing but your final moments over here. Those are nothing but your final moments. Why? because here your distribution is not possible, since the summation comes here equal to 0 over there. If the summation doesn't come 0, then your distribution will continue further, but here it is coming 0, so your table get automatically stop over here, and whatever values you are getting, those will be the values of final moments over there. Okay, then after getting these values, lastly what we will do, we will just write the final support moments over here. That is, we will extract these values from the table and we will write those over here. So first value, that is what, that is for AB, MAB I am getting here equal to minus 75. Next is your MBA, that I am getting as plus 75. Okay, next is your MBC, that I am getting as minus 75 again, and lastly MCB I am getting here equal to 0. All are in kilonewton meters. Here your numerical ends, that is you are calculating the final support moments. Further what you have to do, you have to draw the BMD by superposition over there. Okay, so we will check over there, that is this is your support A, support B, and here you are having support C over there. Okay, sign convention same, those we are using for slope deflection method, negative moment, positive, positive and negative. Okay, so first we will check for joint A, here you are having MAB, here you will be having MBA over there for AB member. Okay, negative moment is occurring over here for AB, so negative it will be plotted on upward side, that is 75. Okay, next for BA you are having positive moment, so again 75 positive on upward side, same magnitude you are having. Okay, next for BC, now whatever moment here you will be having, that will be BC, here you will be having CB. Now check for BC, you are getting minus 75, minus negative upward side, already it is done, and lastly MCB you are getting it equal to 0. Just what you have to do, you have to join this with by using a straight lines over there. Okay, so this will be our plotting of support moments. What is remaining, you have to plot the span moments over there. Okay, so we will calculate that maximum span moments over there. For first span we will calculate that is for AB. AB what is given to you, UDL is given, so maximum span moment for UDL, that comes equal to WL square divided by 8. So if you calculate this, you will get that as 112.5 kilonewton meter. And secondly for BC you will get that as WL by 4, so that comes equal to 100 into L, that is 4 by 4, so you will get that as 100. Okay, so in span AB you are having UDL, so it will follow parabolic path of WL square by 8 is equal to 112.5 kilonewton meter, and in span BC you are having a point load, so it will follow triangular path over there of maximum moment at the center, that is WL by 4 is equal to 100. Just what you have to do here is you have to shade this superimposed part over here. Okay, so this will be your BMD by superposition. BMD by superposition. Okay, so hope so you have understood this numerical over there. If you have not understood, we will continue further with more numericals in this. Okay, this concept is what you have to, firstly you have to understand the concept of the distribution factor, and secondly you have to understand when to do the balance moment and when to do the carryover of the moments over there. Okay, if you are having any difficulties, you can comment me over there. Okay, thank you so much.